You have to understand that performance is about the process. If we just wanted to know how to do this as fast as possible in Java based on things people already know, we'd just go look that up, because you can literally go look at the source code that's in the repository that's like, here is the fastest one that people found, right? So jumping to the conclusion is not interesting, and we wouldn't be doing a series that we just point you to that code and say, here you go, right? The point is to learn the process so you can apply it when you don't already have someone handing you, here is the answer.
Hey folks, and welcome to the 5th episode of Solving Java's 1 Billion Road Challenge together with Casey. Casey, how are you?
I'm good. How are you doing? Apparently, so the news, everyone, is that I guess that we will be sort of putting this series on indefinite hold. We'll talk a little bit more in a second, but because Marco is now in charge of everything, is basically what happened. This is not his fault. When we started the series, he didn't know. So,
I didn't know. You kind of spoiled it. So I wanted to say to you, the viewers, I've got bad news, I've got good news. Okay. Bad news, as Casey just mentioned, is, well, I got promoted into a new role at JetBrains, and my responsibilities increased tenfold, which means I simply do not have the time at the moment to keep the series rolling, even though I really wish I would have the time to do so. So for now, we unfortunately have to put it on hold for the time being. If things change in the near future, then we're going to continue. Other than that, I have to go hop on to the good news. The good news is we still have one episode now today, the Christmas episode, so to speak. Yeah, I would rather get into it then.
Yeah, absolutely. And I also wanted to mention that, like, the stuff that we're doing here is very similar to the kind of stuff that I do on Computer Enhance anyway. And I was thinking, like, I can probably go do some things on there for people who want to see a little bit more of this. I don't know that it would be the best idea for me to do it in Java, because I'm not a Java person, and, that would be like this whole thing of me going and, setting up a Java environment and all that stuff. But I can show how this thing gets optimized normally, and really the process in Java is just trying to just massage Java to output the thing that you would want to output if you were writing it, without a JIT in the way. So there's not really that big of a difference. So just a recap for people who don't remember where we're at, just to kind of explain where we are. So there's two big things that you really want to do when you're working on performance, and now we kind of got both of them. The first one is you want to establish some sort of a baseline, as like we kind of called it before, which is to understand how fast this computer that you're working with, or any computer that you happen to want to target, you want to be able to take sort of a litmus test of that and say, roughly how much performance could this thing do at peak for the task I'm doing? And in this case, because we have to actually read a file and we've been told that the file will be cached, what we're really talking about is, how fast can this operating system deliver a file from a file cache to us? That is sort of, what we would need as a baseline. And so, previous episodes, Marco did some work on establishing that, and it changes per machine. So something you have to run, on different machines if you want to know what that sort of baseline max performance thing you could get would be. And the other thing that we need is the ability to check what's actually being executed. And that's the part where being able to read assembly language really helps, because assembly language is what your computer's actually going to execute. It's the thing that removes as much of the software stack out as possible and just leaves us with what the CPU will do. And so it's really just our way of saying, okay, this takes as many unknowns as possible out of the equation, and we can just look at the actual hardware performance when we're trying to figure out what's going on. And so we actually have both of those now. Marco can take disassemblies, and he can take a baseline. So what we would normally be doing now is starting the process of just iterating on seeing why we fall away from baseline as we do things. That's where we would be at. What we're actually going to do today is kind of more of a wrap-up episode, because we have to put this on hold, but that's where we're at. Does that all sound reasonable, Marco, for a summary?
It absolutely does. Great summary, right? Okay. And maybe just to continue, I had a look at the email thread that the two of us have, and with the last episode, once it closed down, you said, well, the next thing we could actually do is, well, when I go back to BLAS 6 from last episode, we had the code, we went through the entire file, I found semicolons, I found new lines, and then you said, well, let's just focus it a tiny bit more and just run through the entire file and count new lines. And this is what I now put into the BLAS 7 given class here, where literally I'm just take the time that it takes to run through the entire file, check every character, and count the new line characters. That's what I've prepared for this episode. Just real quick.
Yeah, just again, this ties exactly into what I was saying. What we would be doing here, and the reason that I thought this was a good idea, is we would now want to start with sort of the simplest possible thing, because again, and I guess this is good material for wrap episode 2. If all you want to know, because a lot of people, there's people who kind of want to jump to the conclusion, right? There's people who write in and they're like, oh, it's this or that. You have to understand that performance is about the process. If we just wanted to know how to do this as fast as possible in Java based on things people already know, we'd just go look that up, because you can literally go look at the source code that's in the repository that's like, here is the fastest one that people found, right? So jumping to the conclusion is not interesting, and we wouldn't be doing a series that we just point you to that code and say, here you go, right? The point is to learn the process so you can apply it when you don't already have someone handing you, here is the answer, right? And so what we were trying to show on this is the series of steps you would go through to arrive at that correct conclusion. And so this is us going, all right, we can take a disassembly. The reason I wanted to start with the simplest possible thing is we now have to be able to look at the disassembly and verify that we're timing what we think we're timing. Mm-hmm. And there's a lot of reasons why we want to do that. One of them is, for example, the JIT is going to move code around. It might inline things. It might not inline things. It might move the timing blocks to different places. It might include something in the timing block we weren't expecting, or not include something in timing. It may optimize code out completely because it sees it isn't being used. And so the point of trying to start here and having some simple tests that we can start to read and understand is just to go like, okay, let's try to set up a coherent test environment where we can verify we are timing what we think we're timing. So does that make sense as well?
Absolutely, yeah.
So Marco, walk us through what you did for the count new lines here. How does that code work?
So very simply put, we're going to open up a new file channel. We have a buffer of 10 megabytes. Again, Java byte buffer backed by simply an array. We basically read from the file channel into that buffer, so always 10 megabytes at a max. And then we count the new lines on that, backing array. Counting the new lines on that backing array is relatively simple. We have a for loop. We go from 0 to how many ever bytes we have read rather. So it could be 10 megabytes, or at the end, obviously less with the last read. And then we just say, well, if the character, the current character in the array equals new line, then we just go new lines plus, and that's literally it. We sum them up, and we print them out to the console. And when we run this thing, then hopefully we see, after it has finished, we can see 1 billion new lines. Somewhere in the console output. Let me kind of scroll up a tiny bit. And we should see that, it took us 8 seconds, roughly 8.4 seconds, and we found a couple of lines or / new lines. Right.
And so you can kind of already see, hopefully, based on if you've been watching the series so far, you can kind of see where I would be going with this, right? So we know that 8 seconds is too long compared to our baseline if all we wanted to do was read this data in. Right? Because I think you were getting at least something. I don't know if you got as low as 2 seconds over, but it was like 4 seconds or something. Was it even margin, right? Yeah. So again, if we were going to start doing this for real, what we would do is take our baseline. So run that, I think you used DD for it externally to see what it was. And then you had also one in Java that you did. So what we were doing is looking at those baselines and going, okay, we now have already identified a problem. All we are doing is counting \n. This is an incredibly simple thing that the computer, this CPU, especially an M-series CPU, should have no trouble doing at full speed when reading a file compared to just the act of moving the data in, right? And so the fact that we're seeing a very substantial slowdown there, at least 2x, but again, we should actually now, the next thing we do is take real stats and go like, what are the actual numbers? But even just from recollection, we're at least 2x off just to find these new lines. So that to me is the first thing that we would now want to look at. We'd go, let's look at the disassembly. What is accounting for this extra time? Because we need to know what it is. And sometimes, just to be clear, I'm pretty sure in this case this wouldn't be true in this case, but sometimes to be clear, we find out that we haven't really done anything wrong. We weren't thinking about the problem properly. And when we actually flow through and look at what the computer had to do and look at how it has to do it, we realize, oh no, actually that speed is the correct speed. We're not actually slower than we should be, right? So sometimes that does happen. In this case, it's probably not that. In this case, it's probably some other things that we then need to investigate. So that's where we would be at currently. If that seems
it does make sense. And also what I've told you before is, I think obviously I have the assembly output enabled, and you can see it in the console. One more thing is I have hotspot logs enabled, which allow me to pump these hotspot logs into a program which is called JITWatch, which is roughly the Godbolt compiler explorer in the Java world, roughly. And if you want to, I can briefly show it. I mean, we're not going to step through it entirely now, but just so people have seen it once, what do you think?
I think that would be great, and I also kind of want to point out another thing that's a little bit challenging in this situation, which is that we also don't know how much these logs cost us, right? Like, you know, you run something, you have to then also be able to run it with and without this to see if the logs are the thing that's costing you time, right? So all of this stuff, I know it's a lot to take in, but just when you start working on performance, you just always have to keep in mind every extra thing you do is affecting your measurements, and, you know, that's
right.
But anyway,
unfortunately, I can't zoom in here properly, but hopefully viewers can actually see it. You'll find a couple of, if you're interested into JITWatch, you'll find there's hour-long videos of what it can do. But at the end of the day, what I just did is I put the hotspot logs I saved into JITWatch. And now I can get some information here. Information about my class under my specific package, Marco Blast 7. I can see here on the right side, hopefully you can see it here, that we can see JIT compile class members. There was only one method which was JIT compiled, which is my count new lines method. The other ones weren't JIT compiled, right?
And also, I'm assuming, I mean, if I may insert here, because I don't actually know, because I'm not a Java person, but I'm assuming that is because the JIT is effectively watching for call counts and, you know, or things like sampling-based profiling. You know, it'll wake up and go like, oh, it seems like we're spending a lot of time in here.
Absolutely,
I will JIT that. And it doesn't bother with things that you only ran once and that don't account for much runtime and things like this, correct?
Absolutely. Yeah. And that's why they are called hotspots, so to speak. I mean, the hotspot JVM exactly identify hotspots and JIT compile them.
And this is obviously burning through a million lines. It's the only thing the program's doing, really. So it's the JIT's gonna be like, I think it's that guy, right?
Absolutely. What you can also see here is that you can see how often it was compiled, 1, 2, 3, 4, 5, 6 times actually, in different levels. We talked about these. I mean, the tiered compilation back in the day, so last episode, C1 compiler, C2 compiler. There's also something which is called OSR, on stack replacement, meaning the JIT can also, while a loop is running, and it's being interpreted, it can decide, hey, I need to actually compile it, and then replace the current stack, or the current frame rather, with the compile code. That's the on stack replacement.
And that's, I assume, so that it doesn't have to, like, for code that is not super multi-threaded, it can just use a spare core to do the compilation, not stop the thing that's actually running, and then just, once it's got it, flop it in, right?
Exactly, exactly. And it doesn't have to wait until the loop has finished, so we can just do it, right there. You can see, by the way, you can also see when the compile started here, when they finished, how long they took, so all that information you can see nicely inside JITWatch. Now, when you click the method, you get this try view here, and the try view is what is rather nice. Let me just open up a tiny bit. You can see the Java source code here in the left column, where you can see, hey, here is my count new lines method here at the bottom with the for loop. When you click it, in the middle you have the bytecode of that method, right? And on the right side you have the assembly of that method. And I suppose when you go to the right places, right, you get the corresponding lines in bytecode and in assembly.
And again, this is just really, really handy. Like I'm imagining I would probably use this tool a lot if I worked with Java for when I'm trying to do performance analysis. And again, the reason for that is just because you never, once you've worked on this stuff for a while, you realize that there's oftentimes things going on that you might not expect. And they can be things that no matter how, it doesn't matter how experienced you are, doesn't matter how good you are with it. They can be things like bugs in the JIT. Right? I mean, you can literally have like I've had bugs in compilers all the time that I find in C, right? Or in C++. And so one of the other reasons that these tools are so helpful is there's kind of like a heads up view. If you can get one of these quickly, you can also verify that no funny business is going on. So even if it's what you expect, that's valuable information right there because you know there's nothing strange going on. So, so this is really cool. And I guess the thing that I would say is, so maybe, I mean, we have a little bit of time today. So maybe what we could do here is just start to ask the question, where is this extra time going, right? And so to me, the biggest question I have there is like, okay, so this is an M-series chip. I don't program on M-series chips much, but they are very, very aggressive at single-threaded code, which is what we're effectively running here. And I wouldn't expect it to be struggling with this, even if the compilation was a bit naive. So I'm very curious how we're losing this time. And so I'm gonna just ask sort of a maybe this is a big ask, I don't know. Do we still have in this code base here the ability to do sort of the bare read test? The one that doesn't actually do anything.
Which is gonna comment out the counting new lines. So we're down to 1.3 seconds here, right?
So that would be a great thing to now look at, right? We first need to verify, and usually the way that I would do that is by using the assembly code. So like, let's say I was doing this in C, right? I would just be looking in the debugger. I would open it up because that's the fastest way usually for me to look at disassembly. I would open it up. And I would look to verify that my timing code, then the loop has not been optimized out, and that the read calls are in there. We would normally expect that to be true because normally a compiler will not think that it can optimize out something like a read call because it doesn't know all the side effects of an OS call. So it would be very unusual if that were the case. But again, I don't want to sort of teach bad practices. You always verify if you can. If you can't, then you can't. But so I would have always verified that. But let's assume that we did verify that. So what we believe now is that by inserting our count new lines function here into this, literally just that one line, which is the count new lines code below, that just that is sufficient to cause us to drop to basically an 8 close to 8, not maybe more like 7x performance drop, right? Which is pretty brutal, right? So our question has to be, where is that slowdown coming from? Now, this channel read BB that you've got here, is that so that buffer size there that you've got the 10 you got a 10 megabyte buffer there, right?
Yep.
This is going through the file at 10 megabytes per, reading it in, and counting the new lines, right? That's basically what's going on.
Yep.
Now, 10 megabytes is probably, I'm trying to remember the cache size on M-series chips, but it's probably the L2 is quite large on an M2 if I remember correctly. So that may be fitting in there. So the question that we have to ask is like, all right, which of the two things is actually causing our issue? Is the thing that's causing our issue the fact that we are doing computations on this, right? In other words, is it the literal assembly code of load in a byte, because I think it's doing it byte by byte checking, right, is what it's doing at. Load in a byte, check the byte for new line, count if it is, don't if it isn't, right? are we actually spending our time doing those literal operations, those micro operations CPU, or is this just a problem of we're causing more cache misses because, okay, it writes, the operating system writes into this buffer. If no one looks at the buffer, we don't incur any cache misses on this core, which is maybe not the core that the OS did the read on or whatever else happened, right? So it's not in our L1, blah, blah, blah. And plus our L1 would be smaller than, much smaller than 10 megabytes anyway. I think it's significantly smaller than that on an M series chip. So anyway, so a couple of things we could try here that I'm just curious about. So first, let's see how sensitive this performance is to the buffer size. Since we can't go verify the assembly very easily and we have some issues with that, we'll just take a few shots in the dark. What happens if you change that to, like, let's say you change that down to something like 1 megabyte just for fun?
Yeah, okay. Let's see what happens. So 1 megabyte.
Same time.
Same time, right? Yeah.
Try going all the way down to something like 64K.
Right. Let's rerun it.
We could turn all the disassembly off for now too if we want to. I don't know how easy it is for you to do that if it's getting in your way.
We could. Hold on a second. Let me just briefly. And also the that takes right.
Same time basically, right?
Yeah, 500 milliseconds more, but yeah.
So we don't seem to we don't really have any particular sensitivity on this buffer size. I mean, like again, if we were doing this for real, we'd probably want to do a little bit more structured testing than just this. I'm just trying to do what I can do given the context of the stream.
Yeah.
So that makes me kind of wonder, all right, so exactly what's going on with this count new lines thing, unless this is just literally like an unavoidable cache problem, we're now sort of saying like, well, this count new lines actually does seem to be like somewhat of an issue. So I guess I'd like to try something else. Let's put that buffer size back up to what you had it, just 10. We'll just do the 10 times 10, 24. We'll just stay with your 10 megabytes because we don't, I was just playing with that.
Yeah.
So now let's go down and see what happens if we skip. So let's say instead of I equals 0, I less than limit I plus plus, let's go ahead and skip by 16 every time. So I plus equals 16. And now what I'm doing is I'm just seeing like, okay, what happens if we run this loop less, but not enough less that we'd change the caching?
Right.
Just like, okay. So that, now you can kind of see what I'm doing here. I'm using what I have available, right? What I can actually ask you to do.
Yeah.
To figure out what's probably going on. Now, what we saw there is like, all right, if I reduce the number of iterations of this loop, I very quickly go back down to the time that was as if it wasn't running at all.
Right, yeah.
And so again, without verifying more stuff, I couldn't say for sure, but that suggests to me that it has nothing to do with caching or the buffer size because if we're skipping by 16s, cache sizes, typically if you look at, say, an M series chip, the L2 cache is, I believe, typically 128 bytes in the L2 and 64 bytes in the L1. That's what they are like. So if we're skipping by 16 bytes at a time, we wouldn't be changing how many total cache lines we're touching. Right. So we wouldn't expect the cache to be implicated here. We're still asking the CPU fundamentally to move the same amount of data in and out of it, but we are doing less of these checks. We're doing basically 16 times, more when we go by 1 as we do when we go by 16. And so that to me starts to say, all right, we are, for some reason, and this is strange, having a actual execution calculation problem, right? Something is not working properly here. And so the next thing that we would have to do, and I'd encourage you to maybe just, while we're here because it's interesting, let's see where that is. Try the plus equals 8. And 4. So we are pretty sensitive to the number of bytes we're actually checking.
Right, yeah.
Now I'll just point some things out here. we should, if we were going to do this very thoroughly, we should go and say, well, we would like to know, like it would be nice if we could verify that the M-series chip can do this byte by byte if it wants to. And that would be a pretty simple calculation for us to do, and we could do it. But what I would point out is modern CPUs all have the ability to work with at least 16 bytes at a time. So if we wanted to, right, let's say we were busy, because we've talked about this many times. Let's say that what I just did is all the time we have. We're not going to go breaking out the disassembly anymore. We're not going to do it, right? And we're not, because we're out of episodes, right? We already have a very simple solution to this problem. And that is that an M-series chip can load 16 bytes at a time and operate on 16 bytes at a time using, like Neon, basically, like using the SIMD instruction set of the processor. We could literally do a load of 16 bytes, do a single operation which tests all 16 bytes for \n, and then take action just on that, right? And so we already have, even though we haven't really worked this problem through, we've already identified one obvious way you could speed up your program for your purposes, right? It would be literally that. Now, I don't know enough about Java to suggest what is the best way to convince Java to emit such a thing. I'm imagining there's some ways of telling it you would like to do vectorization or something.
There is a new vector API, which is relatively recent, which has come in the last couple of years. And we could actually use it to do these SIMD operations. Yeah, that's what we could do.
So that's one thing. Obviously, we wouldn't have time to do that right now, but that's one thing to look into.
Yep.
Another question that I would have, when we're looking at this particular loop here where we're checking for the array equals \n piece there. So we know, and I don't know to what extent Java will insert, I guess, what I'd call spurious error checking here, because Java is... It's a fairly conservative language when it comes to things like bounds checking, right? Like, it's not like C where it's just like, hey, I can just write off the end of a buffer, and if I happen to own the memory that's after it, that's on the table, right? Java is in theory going to prevent me from doing things like that. Now, in general, I'm assuming, and you can correct me if I'm wrong, but if you look back up at what you had at the top there, you've got this channel read BB -1 loop, and you're doing that flip. You said that the buffer size was 10 megabytes. Does that mean that in general, Java will always let us access that 10 megabytes? And just when you read less than that, it sets just a count to let you know that, but we still have the 10 megabyte backing store?
Yeah, pretty much. That is that limit, right? It tells you then, I just read, for example, I don't know, whatever, how many bytes, but you have the backing array is always these 10 megabytes. Yeah.
So what I'd like to look at then is just, again, for fun, this is not how I would normally approach this problem, because again, I'd normally just work through the disassembly. I'd look at what I thought the thing speed should be, and then I'd make a decision based on that. But because we have what we have, and sometimes that's what you have, right? That's what you have. I'm just going with it. Let's go take a look at loop overhead. I'm just curious what happens. So let's say we go down to that count new lines now. We should be able to step this by 4, like we just did. We ran it by 4, and you ran the program. It was like 3 seconds.
Let me run it again.
Between 3 and 4 seconds, right? It was significantly less than the 8 that we were seeing when we ran by 1. Yeah, so 3 seconds-ish. 3.1. 3.2. Let's go ahead and just check stepping by 4. Let's still get the right new line count. So you look up at new lines now, we'll get the wrong number, right? If you look at where does the found is wrong, right? It's not and that's because it's probabilistically missing new lines. So add 4 checks. I plus 1, I plus 2, I plus 3, so that we get the right answer. It's filling it in for you.
Right.
And see what happens when we run that. So what this tells me, or at least, again, for as best I can determine, where my brain is going, is not loop overhead. It's the actual act of checking the bytes is somehow costing us that much. Now, my guess, because comparisons simply aren't that expensive, my guess is we're seeing something here with the way the array load is going, or something, because it'd be kind of strange if it actually was this much. Now, maybe I'm wrong about that, and this is why we want to go do that assembly calculation. It's possible that this is actually just how long the M-series chip would take to load byte by byte, and you simply need to go the 16x. But this simple check just tells us it ain't the loop overhead, right? There's something weird going there, which I wouldn't have expected it to be, but you never know, right? So that's the next thing we would want to try and calculate. Now, I guess we could maybe do a slight back of the envelope calculation here. And since we don't have much time left, maybe let's do that just to see where we'd be at here at the end of the series. You can get rid of these. You can just flip it back to what you had before.
Yeah, sure.
The array, yeah.
Let's see. Yep.
And then switch that to just its ++ version, kind of the old school. So now let's try and run this again in the way that you had traditionally. Can we look at that disassembly one more time there?
We can.
Old school. Is that still available? So now let's take a look at that count new lines, and just click on that new lines ++, for example. That will give us. That should put us right in like the sort of middle area of that loop.
Yep.
Right. At least that's what we would expect. So when we take a look at this code right here. I don't really know how accurate it is when you click on these things, but like, for example, let's say you clicked on the array I equals /n, right? That's a comparison. And on the side, you can see kind of on, you can see on the side there, it's kind of got, that's a load that it's doing, right? That LDR there, it's loading data in, to a register, W11 in this case, I assume. Although, again, caveat to everyone, I don't program in this assembly language, right? I don't use ARM assembly, so I'm just kind of going based on the fact that you can sort of read, you could sort of read assembly languages if you've read one, maybe would be the way to put it. I don't know. Anyway. So if we take a look at what the code is doing here, right, it's kind of hard to see where the loop actually is just from what this has picked out. Those B, so if you look at where those B's are, there's just like single things that say B. Those are where your loop points are going to be. Those are branches. Like the B is branch in ARM assembly. It would be they're usually written differently in x64. They'd be JMPs usually, or J and then something. And so these branch points are the places we would be looking at to try and figure out where our loop actually is occurring. And so the question is, when we're looking at this, it's a little annoying because we're like, okay, we're not sure exactly which of those branches account for it. Maybe, right, the for I loop goes down to that branch down at the bottom there, or maybe it's some of this stuff down. There's like this a bunch of comps down at the bottom, right? And when we're first looking at it, it's a little bit hard for us to tell exactly where, which is the actual thing that we're looking at. And this is also, by the way, one of the reasons, just to give some perspective on why people like me would usually prefer not to have to work with Java, is one of the things that makes it a lot easier for us is, okay, now I've got to sit here and read that. That's what I'm going to do next in order to try and figure out, to make sure I've got which loop is actually the loop. Right? I'm assuming it's this part, and that like C cell and stuff there, that's doing like the, okay, did the comparison work or not? If it is, then I'll do this, this add or whatever, things like this. I don't know yet though, right? And so I have to go read that. If I was doing this with ahead of time compilation, which I guess Java is not as common or whatever.
Yeah, not as common, yeah.
But if I was doing that, like in C, it's all ahead of time compilation, I just load up with the debugger, I just hit break, and I'm right in the loop. And I can hit F10 and watch the loop run. I don't have to read the assembly at all to know that I'm inside the loop, and I can watch the body of the loop that's being executed, right? So it saves me a ton of time, especially in a situation like this where I don't normally read this assembly language and I might make a mistake. Well, that takes all of that possibility away. I can literally watch the thing running. And so that is a really nice feature to be able to have access to, whereas here we don't. So, but anyway, if we were to read this down, and let's assume that we were going to say that this is the actual loop body that we're looking at, that we're actually looking at here. So the branch, you can see there's these bees. It's annotated them with where it thinks it's going to branch back to. Right, you can see line 45, line 44 there, and if I don't know, if you scroll the source to the left slightly, it's missing the line number, just the line to the left slightly.
Sorry.
There you go.
Sorry. Yeah.
Right. So you can see that branch that says count back to line 45. Right. That would look like our loop to us, right? Because line 45 is the actual loop we would expect that to be going, right? And so I might imagine that the loop, I'd look a little bit up here and just say, is the loop here are these bees above us? Are those actually the loop body and not this thing that it's picked below us, right? That would be my first guess, because I'm like, I don't see the obvious branch down there. However, it could also be that this branch, you see there's I can't point at anything. Yeah. You see there's a comp, there's a LDRSB W10, and then a comp W10, then a branch back to line 45. That could also, be it too.
Right.
So which part of this is running most frequently and how? On a stream where I'm just faced with this assembly in 10 seconds, I'm not going to be able to tell you exactly what's running.
Right. Yeah.
But what I can say is, let's suppose it was the thing that it's highlighting right now. Right? Like, meaning it is this block that we're in with a lot of instructions. Even just without doing any kind of more aggressive microarchitectural analysis, when we think about how fast this chip is running, right? You've got this, you're running this on the laptop or the...
laptop, yeah. Laptop,
yeah. And the laptop is an M2?
It was, and then let me just quickly double check. No, it was an M3 Max.
So you see on the left there's this big hexadecimal number. Presumably that's some sort of address that is like where this code is located, or at least, a nominal address, meaning maybe that's not really where it's located in memory, but it's where the JIT is thinking of it as being located before it rebases it. I don't know. It looks like a legitimate address, so it might just be where this code actually was at the time, right? And anyway, that code, that address is going up, as you can see, by a very regular number. That's because this particular instruction set, ARM, is typically fixed size instructions. They don't the instruction sizes don't vary very much. Like they do in x64, they're variable length instructions. So you can see the addresses go up by 4 every time, and that is the size of the instruction being encoded. Does this make sense? Like,
it makes it. That's right. Yeah.
So normally what we would see, and that's literally the memory layout, and then that, the instruction that's printing there is just literally decoding the bytes of the ARM instruction and turning them into something we can read. So normally what I expect to see after a branch, right, is I would expect to see like something that said where the branch went to. And you can see that it's commented on in various places, but it doesn't seem to say. Like it doesn't. And so my question is, like for example, there's a branch down at the bottom that does say where it's headed, and then the other ones don't. And I'm wondering if that's maybe just like, that's because, Casey, like if you knew ARM, right? It's because the branch value gets loaded in, differently, right? Like you can imagine that being the case. For example, do you see that CBZ W11, and then there's a big thing after it, right?
Yeah,
something like that. You could imagine like, we load in where we're going to branch to in this other way, and so you have to have just tracked it. Like we can't annotate the disassembly with that for you because of reasons, right? So I don't know exactly, but let's say that we were taking a look at this and we wanted to ballpark, and we wanted to say, looking at the instructions there, let's suppose this actually is representative of the size of the loop that this thing is actually doing. I'm looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, somewhere around 14 instructions or something like that. And so if we took the total size of this file, which I think you can get for us, right? If you go just do a ls minus al or something on the file, you could get the size, right?
Yeah.
It's right there. Yeah. So it's like, around 13 gigabytes, right? Something like that. It's, so if I was to type this in, I'll just ballpark with 13 gigabytes. So if we said we have 13 gigabytes here, which is going to be, 13 billion plus bytes. More like 14 billion bytes. We know that we're going to try and execute 14 instructions, maybe, if that was the loop, if we were actually looking at it correctly. That gives us a total number of instructions that we have to execute to run this program for just that loop, right? If that was correct, and we haven't determined that is, right? That looks too large to me, so I'm thinking it's not, right? But I'm just, so who knows, right?
Yeah.
And, maybe it could have unrolled something, who knows? So we'd have to go through and read that. But the way we would do this is, so we'd take 14, and you could do this on a calculator with me if you want. I'm doing it here on my own, but.
Yeah.
So let's take our roughly 13 billion, or you could even, if you want to be more precise, copy that file size, right? And multiply it by the 14 instructions that we saw there roughly, right? That's how many instructions that we would need to execute in order to run this thing. Now, we know that we're taking 8 seconds to run it, right? So if we just divide this by 8, we'll get a ballpark number, right? That is right there. And is there any way to get separators? It's kind of hard to read, but okay, so like say then another one, 241. Right? Is it sorry if I get it right? So yeah, how many actual?
1, 2, 3,
24
billion. Yeah, 24 billion. Yeah.
So we're basically saying this would have to do 24 billion instructions a second in order, that's what we would be expecting it to be doing to see the number that we've got. And so the question is, well, what's the clock rate of this CPU, right? It's definitely not above 4 billion. Let's suppose even that this thing was running at a very high clock rate for a M-series laptop that, I don't think they make 4 gigahertz versions of an M-series chip. I don't think that exists. I mean, I could be wrong about that. Maybe it does. But even at an Intel, a server kind of clock speed, right? If we were to divide that, we would find that this thing, if we were to divide it by, let's say that 4 billion or whatever, what we need to know. I must look it up. What is a peak clock rate of an M3 Max?
Let's find out.
This is known information. This is not a difficult thing to determine, right? Do they really is this something that Apple obscures that surely people have determined what the clock speed is, right? 4 is a good guess, 4 gigahertz. I would say that's a safe bet. This is a ballpark calculation anyway. So if we were to divide this by 4 gigahertz, right, which is just 4 times 1,000 times 1,000 times 1,000.
9 zeros, right?
Yes.
Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, right. Okay.
So there we have what we would typically call our IPC number, our instructions per clock. So on every clock cycle, this M-series chip would have to be issuing 6 instructions. Now, an M-series chip, believe it or not, can do that, right? I believe they can sometimes get as high as 8. I think they have 8 decoders. So they could go as high as 8 sometimes. But when I look at that number, that is very aggressive. So to hit that 8-second target, we would be asking, if that was the loop, we would be asking this thing to hit a sustained instructions per clock of 6 instructions retired every clock cycle, right? Which is very aggressive. And so if we went and took the time to verify that that is the loop that's actually running, which again isn't hard. If you give me an hour, I could go read that whole disassembly. And again, not knowing ARM disassembly, I'd look up some things, right? I'm not going to read it straight like I would x64. If that actually is the loop, this is too aggressive. So we know right away our first line problem is actually before fixing read bandwidth, before looking at cache, before any of those things, our problem is too many instructions. Too many instructions. We have to convince the JVM to output a more efficient loop. The easiest way to start with that, probably, like I said, rather than trying to get it to do a more efficient scalar loop, is just to switch to SIMD and get that 60. That would be my first line. And I think with that, we're out of time.
Right. Cool. So then, thank you very much. We're going to keep it at vectorization. If we're going to come back, we're going to tackle that next. Thank you for the explanation. Thank you, Casey, for the past 5 episodes. And hope all of you viewers had a good time.
Yes, and I would love to do more of this. I love this sort of thing. And also, like I said, I'm happy to take over this a little bit. I would like to know the answer to some of these questions, so I may take this up on my website and just kind of follow it through a little bit more because I would like to know. It looks to me like, really, surprisingly, this is just a case of you need a more efficient way to check. That's what we would need to start doing. So.
Right, yeah. Okay, cool. Then thank you very much, folks. Bye-bye. See you next time.
Have a good one.